All right, 3.4 measures of position and outliers. So, in today's lesson, we're going to talk about ways of describing where a single data point is found in a data set. So, is it near the top of the data set? Is it near the bottom of the data set? Is it in the middle? Where does a value find itself, or where do you find a data point in a data set? Um, some of this stuff you'll be familiar with, some of this stuff will be new. The most common place you've seen these types of things is when you take a standardized test. On a standardized test, and I'll get a little bit more into this, they use percentiles. So you're used to seeing something where if you took your ACT or SAT and you got a raw score of 700 on the math section, they then turn that into like, oh, you're in the 90th percentile. And so we'll talk a little bit more about percentiles later in this chapter, but that's the type of thing we're going to be dealing with in this section here. And the first one we're going to talk about is a z-score. So a z-score is a unitless measure of distance from the mean. So it tells us how far away from the mean, theoretically the middle of our data set, if it's a normal distribution, how far away we are in terms of standard deviation. So are we one standard deviation above the mean? Are we a half a standard deviation above the mean? So it gives us a way of talking about how far above or below average we are in terms of standard deviations. One of the really nice things about this, there's two really nice things. One, it allows people to compare things against kind of typical, against the average. You'll find z-scores used a lot in infants if you ever have a child or when your parents had kids. After birth, you go in regularly to see a doctor. So I think it starts off, you see them once a month and then once every 6 weeks, but you see them a lot. And every time you go in to the doctor, they take height, they take weight, and then they do a head circumference. And then they take all that information and they plug it into their system and it spits out a z-score. So how tall is your child compared to every other child, essentially, in the world, depending on what database they use. Some of the information, or most of the information, comes from the World Health Organization, WHO, and it kind of tracks the averages of heights and weights and head circumference for different age kids and allows you to see kind of where your child is. This is most commonly used for children that are on the lower end of that. There's a condition called failure to thrive, which means for some reason those infants aren't growing the way they should be. And so by taking these measurements, they can find out, hey, this baby or this infant is significantly lower in the weight category or the height category than they should be. Let's make sure we bring that infant in and give it some special help. So do we need to monitor how much it's eating? Those types of things. The other thing you can use it for is to compare two different populations together. So my favorite example is using myself. It's using height and Mrs. Hamilton. If you don't know her, she's a Spanish teacher here at Arapahoe and a volleyball coach. So it allows us to compare things. So I am taller than Taylor. I'm like 6'2". She's tall. I don't know how tall she is exactly, but she's a tall person. So if you just said, who's taller, you or Miss Hamilton, I am taller than Miss Hamilton. However, for our population, so am I taller compared to the average male than Miss Hamilton is for the average female? And we can use a z-score to compare our two heights. You would start out by looking at, okay, well, the formula to find a z-score says you take your data point, so your height, and then you subtract the average. So that tells you how far away from the average you are. average height of men in America is about 5'9". So you would take my height and subtract 5'9", and then divide by the standard deviation of the height, which I believe in America is about 2.6 something inches. And so you divide those two things, and that is the standard deviation. And so you'd come up with a z-score. And because I am taller than the average person or average male, I would have a positive z-score. Then you would do the same thing with Miss Hamilton. You would take her height, let's call her, I don't know, 5'11". So she's 5'11", and you'd subtract the average height of women, and the average height of women is significantly less than the average height of men. It is 5'4". So the average height of a woman being 5'4", you take her height, subtract that 5'4", and then divide by the standard deviation. And I believe the standard deviation for women is roughly the same as it is for men. I believe it's right around 2.5, 2.6, something like that. You do that division, and you would get her z-score for her height. Then you could compare the z-score for me and the z-score for Miss Hamilton, and whoever had a larger positive z-score would be taller relative to their population. So the idea would be if you put 1,000 women in a group and 1,000 men in a group, and myself and Miss Hamilton were in our groups, she would stand out more than I would stand out in my group. And that's what z-scores allow you to do. Compare two different populations together to see how much above or below average they are based on their population. So you're not comparing absolute, you're comparing relative to their population, which is really nice. All right, so let's go through this, and then I'll talk about two things that a z-score actually tells us when we do this problem. So here's our example. We have the mean resting pulse for men is 70 with a standard deviation of 8. A man has a pulse of 80. Find the z-score and interpret the answer. So X is the data point that we have, which is 80. X bar is our average, which is 70. And then our standard deviation is 8. So we plug that information into our formula. So we get 80 minus 70 divided by 8, which gives us 1.25. So our z-score is 1.25. That's the first part. Now, the second part of this question says, interpret the answer. When you are asked to interpret the answer, you're essentially writing a sentence, and that sentence needs to contain two pieces of information. First, it needs to tell how far away from average. And the second, it needs to say whether it is above or below average. So for this answer, that 1.25, we would write the man's pulse is 1.25 standard deviations above the mean. So the two key pieces of information, we are saying, the two key pieces of information, first we have to say how many standard deviations it is away from the mean, which is that 1.25. So we're 1.25 standard deviations away from the mean. Now, are we above or below the mean? That is the second part. And so since it's a positive z-score, it is above the mean. Now, the other thing to realize is that a z-score is not inherently good or bad. So having a negative z-score or having a positive z-score isn't a good or a bad thing. It is simply a thing. It's just telling you information. Depending on the context of that, you'll either want to be above or below average based on the context. Height is simply a number. It doesn't matter whether you're positive or negative, that's simply saying, are you taller or shorter than average? If you are trying to lift weights and you're comparing how much you bench press versus someone else of a different gender or of a different age range, something like that, those are different groups you could compare. And if you're trying to lift more weights, having a positive Z-score is going to be better. If I bench, I don't know, if I lift weights and I'm trying to be stronger, being able to lift more above average is going to be a good thing. So you want a positive Z-score when you're comparing how much weight you can lift. However, if you're in track or swimming or some sort of timed event, being negative, being below average is what you're looking for. If you are running a marathon, the further below average means the faster you're running your marathon. So that's what you would want. So again, saying positive or negative is not a value judgment. You're not saying it's good or bad. You're simply saying above or below average. And depending on the situation, you could want to be above or below average based on that. And then when it asks you to interpret your answer, you need to tell me how far above or below average you are in terms of standard deviations. And you need to tell me whether you're above or below. So those are the two pieces, the magnitude and whether you're above or below. All right, that is Z-scores. We come back to Z-scores starting in chapter 7 and 8, and then we use those Z-scores a lot through the rest of the semester. Percentiles, that's the one I talked with you about at the very beginning. It's the most common. When you talk about a percentile, if they give you a percentile, so you got a 700 on the math portion of your SAT, and that puts you in the 88th percentile. That numeric value, that 88th percentile piece, tells you how much of the population you did better than or equal to. So if you are in the 80th percentile, that means 88% of the people that took that test got the same score as you or below. And now there's a couple different ways of mentioning percentiles. One way is to flip kind of the direction you're looking. So the 88th percentile means you're better than or equal to 88% of the people that took it. Or you could say the top 12%. So when you throw that word top in front of your percent, that changes the direction you look at. So the 88th percentile is same as saying I'm in the top 12%. If you're in the top 12%, that means 12% of the people did as good or better than you. Just like the 88th percentile says you did better than or equal to 88%, it just kind of changes the direction you're looking, either below you or above you. And you can use those either way. Most commonly, it talks about the people that are less than you. So the higher percentile means the better you did. You'd rather be in the 99th percentile than the 91st percentile. That means you scored better than more people. So when we talk about interpreting the 80th percentile, that means 80% of the people that took the test, I guess we don't know if it's test, 80% of the data values fall at or below. So if you're in the 80th percentile, that means 80% of the data values fall at or below whatever we're looking at. At or below our data point. Then it says interpret the median as a percentile. So if the median is right in the middle, which percentile would that be? So our median is the 50th percentile. Now we're going to look at quartiles, and quartiles, similar to percentiles, it just cuts, there's less of them. So there's 100 data points in a percentile, or 100 values in a percentile. You can be the first percentile all the way through the 100th percentile. When we deal with quartiles, there are 3 quartiles. So it cuts the data into fourths, and there are 3 of those division points. Q1 separates the lower 25% from the rest of the data. Q2 cuts the data directly in half. So Q2 is our median. And then Q3 cuts the lower 75% off from the upper 25%. So when you look at this picture where we have our Q1, Q2, and Q3, what that tells us is that 25% of the data is in each of these little sections. So the sections don't have to be equidistant or equally spaced out. It has to tell us where the data lies. So if Q2 and Q3 are really close together, that means there's a lot of data in that interval. Whereas if Q1 and Q2 are very spread out, that means there's not that much data, so you have to have a larger range of values. And then when it says find your Q1, Q2, and Q3, you essentially go through the process of finding a median, but you do it 3 times. So first you cut your data in half and you find the median. That's going to be your Q2. And then once you've found Q2, you find the median of the lower half of your data and the median of the upper half of your data, and that's going to give you your Q1 and Q3. You can also put all of your data into a list, and when you do your one variable statistics, those also give you Q1, Q2, and Q3. So that's another way of finding that data. So we are going to, by hand, find Q1, Q2, and Q3 of this data set. So the first thing we have to do is we have to make sure that it is sorted. So we have to make sure that the data is in ascending or descending order before we start finding it, because we're finding medians, and that's our first step in finding a median. And then we have to count, and it is an odd data set. Because it's odd, that means there is exactly one middle value. In this case, it's 17. So that's going to be our Q2. Then we find the median of our 2 different sections. So that median cut our data in half. Now we find the median of our upper and the median of our lower data set. So this is going to be our Q1. That's going to be our Q3. So Q1 is 14. Q2 is 17. Q3 is 20. All right, let's do it again. Now, this time, hopefully you've paused it and tried to find them on your own. This time it's a little bit different because our data set is even. So because our data set is even, we have to find the middle, but there's 2 middle points, and our middle is going to be in between there. So to find the median of an even data set, we add the 2 middle parts and divide by 2. That gives us 8.5. That's our Q2. Now, because I didn't actually use the 8 or the 9 for my median, those values get included in my lower data set. And my upper data set. So that 8 goes into the lower data set, the 9 goes into the upper, because I didn't actually use the 8 or the 9. Up here, the 17 was my median, so I took it out of the data set. Here, I didn't use the 8 or the 9, so they get divided into their own little groups. And then I go ahead and find the median for the lower set and the upper set. And again, we still have even data. And so I have Q1 is 3, Q2 is 8.5, and Q3 is 11.5. And that's how we find Q1, Q2, and Q3. We use Q1, Q2, and Q3 when we do our 5-number summary, which we'll talk about in 3.5. But we also use Q1 and Q3 to determine our IQR, which is our interquartile range. Your IQR, when you find it, can be used or is used to measure the distance between Q1 and Q3. So it talks about how spread out the middle of our data is. So it's another way of talking about spread. And this measure of spread is resistant. So the most common measure of spread we have, standard deviation, is not resistant because it looks at every single point. So if you have an outlier that's really, really big, along with affecting your mean, it will also affect your standard deviation. So when you're looking at measures of center and spread, usually we have mean and standard deviation, and those typically go together, and they are not resistant. So an outlier will greatly affect the mean and the standard deviation. If you have nice, neat, normal data, the mean and the standard deviation work great. However, if you do not have nice, neat, normal data, if you have outliers, if your data is skewed, you would most likely use your median for the center and the IQR for the spread, because both of those measures are resistant. And so if you have data that's not nice and neat and normal, and you have outliers or it's skewed, you'd want to use statistics that are resistant to those outliers. And that's what the mean, or that's what the median and the IQR are for. If the data is nice and neat and normal, the mean and the standard deviation can be used because we don't have those outliers. All right, so back to the IQR. The way we find it is very simple. It is simply Q3 minus Q1. We're just finding the range of the data between Q1 and Q3, which gives us the spread of that middle 50% of our data. And we use that IQR in order to determine if something is an outlier or not. So the IQR is used to determine if we have outliers. And this is how we find it. This is the formula for it. We find the IQR, which is that range of the middle 50%. We then multiply that value by 1.5. And then we add it to our Q3 and we subtract it from our Q1. And those numbers give us our interval. Anything that falls within that interval is going to be considered a normal value. Anything that is outside of that interval is considered an outlier since it's outside of our interval. So those are the 5 steps on how to find your upper and your lower fence. That's what those values are called. Upper fence, obviously the highest value, lower fence, the lowest value. Anything inside of our fences, okay. Anything outside of the fences, outlier. And here is our example. So suppose that breakfast cereal sodium data had the following data points. So we have a Q1 of 145 and we have a Q3 of 225. Determine our upper and our lower fence. Take a second, use those 5 steps, find me an upper and a lower fence. All right, so first thing we have to do is actually find our IQR, which is going to be 225 minus 145, which gives us 80. So our IQR is 80. Next, we actually find our upper and our lower fence. That's going to be step 3. So step 2 is the IQR. Step 3, we're going to take our IQR and multiply it by 1.5. That's that 120. Then for step 4, we do Q1 minus 1.5 IQR. So that's 145 minus 120. That gives us 25. That is our lower fence. For our upper fence, we do Q3 plus 1.5 IQR. So 225 plus 120, 345, and that is our upper fence. So essentially what we have now we have created an interval, and anything between our 25 and our 345 is an okay value. Anything outside of that is considered an outlier. And then it gives us a couple data points to check. So would an observation of 50 be a potential outlier? No. And why? Because 50 is greater than 25 and less than 345. So it is in our interval. That would be because 400 is greater than 345, which means it's somewhere out here, which means it's an outlier. So the 50 was in here. That's good. Outside, not good. All right. And that is the end of 3.4. Again, as you're going through doing your homework, watching the video, if you have any questions, please use that homework help form and let me know.